Good evening, everyone. This is Mr. Kong. I'll be talking to you about section 5.5 in the new chapter. We'll be looking at two important theorems for polynomial functions and their roots. The first theorem is the rational roots theorem. I know that a lot of you probably feel more comfortable seeing my face while I teach, so I'll go ahead and appear on the screen. There I am. Great. The first thing that we want to take a look at is something called the rational roots theorem. Here's what the rational roots theorem says. If a polynomial function has rational zeros, we also will call those roots, then those zeros would appear in a list created by dividing each factor of whatever the constant term is in the equation by each factor of whatever the leading coefficient of the polynomial is. We often will call the constant p and the leading coefficient q. So what I want to do is create a bunch of fractions in the form of what we call p over q. Let's take a look at what I'm talking about. In this example, I'm going to list all the possible rational zeros of the function 6x cubed plus 2x minus 18. All right, what is the constant in this problem? It's negative 18. What is the leading coefficient? It's 6. I'm going to list out all the factors of negative 18, including the negative factors, and all the factors of 6. I've got positive negative 1, positive and negative 2, positive and negative 3, positive and negative 6, positive and negative 9, positive and negative 18. Those are all the factors of 18. Now I'm going to divide each of those numbers by each of the factors of 6, which are positive and negative 1, positive and negative 2, positive and negative 3, and positive and negative 6. Now, the way I do this is I take each top factor and divide it by each bottom number one at a time. So let's see here. I'm going to do, for example, positive and negative 1 divided by positive and negative 1. Well, that would give me positive and negative 1. Then I'll take positive and negative 2 divided by this positive and negative 1. That would give me positive and negative 2. As you can see, by dividing all these top factors by 1, I just get that top list again. Positive, negative 1, positive, negative 2, positive, negative 3, positive, negative 6, positive, negative 9, and positive and negative 18. Now what I'm going to do is I'm going to now take this factor, each top factor, and divide it by the 2. So I would get positive and negative 1 divided by 2 is positive and negative 1/2. Then I'm going to do 2 divided by 2. Well, that's positive and negative 1. That's already in the list. I don't need to list it again. Now I'm going to do positive and negative 3 divided by 2. All right. Then positive and negative 6 divided by 2. Well, that's positive and negative 3. That's in the list. I don't need to list it again. Positive and negative 9 divided by 2. Oh, that's not in the list. That needs to be in there. That's positive and negative 9/2. Then I do positive and negative 18 divided by 2. That's positive and negative 9. That's already in the list. I don't need to list it again. Now I'm going to go to the 3 on the bottom. I'm going to divide each top number by 3. By doing this, I'm going to get positive and negative 1 divided by 3 is positive and negative 1/3. Then I would get positive and negative 2/3. 3 divided by 3 is 1, already in the list. 6 divided by 3 is 2, already in the list. 9 divided by 3 is 3, already in the list. And 18 divided by 3 is 6, already in the list. Now, the last number I have in the denominator that I need to make fractions with is the 6. So I've got positive and negative 1 divided by 6 is positive and negative 1/6. Well, 2 divided by 6 is 1/3. I see that in the list. 3 divided by 6 is 1/2, already in there. 6 divided by 6, 1, done that. 9 divided by 6 is 3 halves. It's in there. And 18 divided by 6 is 3. That's already in the list. So what I'm trying to tell you in this is out of all these numbers, if this function has any rational zeros, those zeros would have to come out of this list. Okay, now take a look at the next part of this. The next theorem is called the conjugate roots theorem. Basically what the conjugate roots theorem says is if you have a square root or a radical that's a 0, you know that he always will come in a pair. One positive and one negative. The same thing is true for your imaginary zeros or complex zeros. If a positive I is in your problem as a 0, so will his negative form. Take a look at how easy this is. Suppose I'm given each 0 and I'm asked to find another 0 of the polynomial function. Watch what I'm going to do. Well, I know if I'm told that 3 minus the square root of 2 is a 0, what can we assume according to this? Well, 3 plus the square root of 2 must also be a 0. In the next example, if 4 plus 5i is a 0, what must be a 0? 4 minus 5i. I could assume that that would also have to be a 0. Now notice, what this theorem says is the opposite of the radical or the opposite of the imaginary number. That's what you have to take the opposite of. Do not take the opposite of the real part to create the partner or pair that would also be a 0. Well, that's it for now. Hopefully this helps explain this section, and we'll talk to you later.